Page 11 of Complex Numbers and Polynomials. Page 191 reading, we're going to talk about polynomial equality. This is a pretty basic concept. So if you have two polynomials, they're equal if they have the same degree and the corresponding terms have equal coefficients. Does that make sense? So like, for example, the polynomials have to be the same length. They have to have the same highest order. Every single one of the terms has to have the same number in front of it. That's the coefficient. Okay, so I'm going to write down here. They have to have the same degree, which is the n value. And they have to have this equal coefficients, which is the number that's multiplied times the variable. That's intuitive, right? Number 1 from D2. Find constants a, b, and c given that these two polynomials and their quadratics are equal to each other. Well, this just becomes an algebra problem, right? Because basically what this is saying is that the two orange coefficients are the same because we're saying that the entire polynomial is the same. The purple are the same, and the brown are the same. So right off the bat, we can say that c equals 5, right? Because the brown terms are equal to each other. C and 5 are equal to each other. We can also say that a equals 2 immediately because the orange coefficients are equal to each other. Then we know that 2b minus c, which is the purple coefficient here, is equal to 4, which is the purple coefficient here. So that means that, 6, sorry. 6, 2b minus 6 equals 4. So let's solve for b using algebra. So we add 6 to both sides and we get 2b equals 10. b equals 5. And so we have b equals 5 and we have a equals 2 and we have c equals 5. All right, that wasn't too bad, was it? Let's go to b. So b, we got, this is a little bit more complicated, isn't it? Because this is not in the form where you have each term separately. So we can't use the definition of equality of polynomials yet. So let's do this. First, we're going to multiply this out. We're going to multiply this one out, and then we're going to arrange it so that it looks like this, where all the terms are separate and added together. So first, let's do x minus 1 quantity squared. So we get x squared minus 2x plus 1. And then we multiply that times 2x plus a. So that would be 2x cubed minus 4x squared plus 2x. And then we multiply times a. So we get ax squared negative 2ax and plus a. And then we get 2x cubed plus a minus 4x squared plus 2 minus 2ax plus a. Okay, last of all, we're going to add in this part of it that we haven't added in yet, bx plus c. So we'll put the bx plus c here. So we can see now we have a complete picture. It's 2 minus 2a plus b times x plus, and the last coefficient would be a plus c. And then we have the first two coefficients here, right? So let's match up the coefficients. So 2 is 2. That's good. Negative 1 is equal to a minus 4. Plus 6 is equal to a plus c. And 2 minus 2a plus b is equal to 0. So right off the bat, let's see, we're going to do a minus 4, which is the brown coefficient, equals negative 1. So a is equal to 3. Okay? And a plus c is equal to 6. But we know that a equals 3. So c is equal to 3. also. And now we can solve for b also because we know a. So 2 minus 2a plus b is equal to 0 because the green coefficient is 0. We know a equals 3, so 2 minus 2 times 3 is 6 plus b equals 0. B equals 4. Is there any other variable that we need to solve for? A, B, C. That's it. Show that z to the fourth plus 64 can be factorized into two real quadratic factors of the form z squared plus az plus 8 and z squared plus bz plus 8, but cannot be factorized into two real quadratic factors of the form z squared plus az plus 16 and z squared plus bz plus 4. Okay, so let's do this. Let's take this and this quadratic, and we're going to multiply them together. I'm going to do it with lattice multiplication, okay? Z squared plus AZ plus 8, and I'm going to multiply that times Z squared plus BZ plus 8. And this will be Z to the fourth, and this will be BZ cubed, and this will be 8Z squared, and this will be AZ cubed, and this will be 8Z squared. This will be ABZ squared, and this will be B8BZ, and this will be 64, and this will be 8AZ. And then I'm just going to add the diagonals, right? So this will be 64. This will be 8A plus 8B, Z. And this will be 16 plus ABZ squared. And this will be A plus B, Z cubed, and then Z to the fourth. Let's see. Then we compare that to Z squared plus 64. So the Z squared corresponds to that, right? Just 1. And the 64 corresponds to 64. What about all the others? So everything else is going to add up to 0 according to this, because z to the fourth plus 64 has no other coefficients. So that means a plus b equals 0. That means 8a plus 8b equals 0. But remember, 8a plus 8b equals 0 is the same thing as a plus b equals 0. So this doesn't add anything else. And then 16 plus ab equals 0. So we know that a equals negative b because a plus b equals 0. And we know that 16, if we substitute in negative b in there, we'll have 16 minus b squared equals 0. So that means that b is equal to either 4 or negative 4, right? And if b is equal to 4, that means a is equal to negative 4. And if b is negative 4, then that means a is positive 4. So looks like we have two solutions. We have the negative 4, 4, and we have the 4, negative 4 solutions. All we need to do is like plug those back into here, and that'll give us a pair of possibilities, right? Those two quadratics, if we put like 4 here and negative 4 here, that would multiply together and give us z squared plus 64, for example. Okay, or if we put the opposite, negative 4 and 4, but that would be the same pair, right? Now they want us to show that this pair multiplied together cannot give you z to the fourth plus 64. So let's try that one. So let's make a grid again. And so one of them is z squared az 16, and the other one is z squared bz plus 4. And then, so we'll multiply these out. So this is 64, this is 16bz, and this is 16z squared. And this is az cubed, this is abz squared, and this is 4az. And this is z to the fourth, and this is bz cubed, and this is 4z squared. So this would be z to the fourth, a plus b z cubed, 20 plus ab z squared, and 4a plus 16b z plus 64. Okay, and let's see. We know that the 64 matches, and we know that the z to the fourth matches. So now we just need to write equations for all the rest. So we know that, like, the z cubed term, a plus b, has to equal 0, right? So like before, we know that a equals negative b, right? Then we take this one here, 4a plus 16b equals 0. So 4a equals, 4a minus 16a, because I just substituted in for b, I put negative a, equals 0. So that basically means that negative 12a equals 0. So that means a equals 0. If a equals 0, then that means b equals 0, because a is the negative of b. And now let's try to plug it into the very last equation, which is 20 plus ab. So that'd be 20 plus 0 times 0 equals, can that be 0? It can't, right? Because like this 20 here is always going to be 20, and this is 0, so they can't equal 0. So that means that these two polynomial pairs cannot multiply together and give you z to the fourth plus 64, because that just doesn't work out. There's not an A-B combination which is going to make that happen. So fail. All right, and that's the end of this page.